Assalamu alaikum everyone, welcome back to the channel Let Us Science Explorers. I am Sarah Javed. Today we are diving deep into a fascinating and highly relevant machine learning challenge, the Dig4Bio RAMan Transfer Learning Challenge. This competition hosted on Kaggle tackles the critical real-world problem in bioprocess monitoring and chemical analysis. It's all about making machine learning models work across different scientific instruments, a concept known as transfer learning. So, what exactly is this challenge about? At its core, the Dig4Bio challenge leverages Raman spectroscopy, a powerful, non-destructive, and relatively low-cost technique used to identify the chemical composition of samples. It's becoming increasingly vital in bioprocess engineering for real-time monitoring. However, there is significant hurdle. Models trained on data from one Raman device often fail when applied to data from another, even if they are measuring the same thing. This is due to subtle differences in hardware and signal processing between instruments from different vendors. This challenge directly addresses this problem. So the main goal is to build a machine learning model that can accurately predict the concentration of three key analytes, glucose, acetate, and magnesium sulfate from Raman spectra. The twist: you need to train your model on data from 8 different Raman spectrometers and then make it generalize to a brand new measurement setup with minimal additional data. This is the essence of the transfer learning problem. Alright, now let's talk about the dataset. The competition provides a unique dataset of over 2500 Raman spectra. This includes data from the 8 different devices used for training, all collected under the same experimental setup. For the transfer learning part, you also get a single 96 well plate measured on a new Raman system with a multiplexer. Your model needs to perform well on this new unseen instrument. Submissions are scored using the coefficient of determination R square score, which measures how well your prediction aligns with the actual concentration of the three compounds. A higher R2 score indicates a better performing model. Now let's break down the provided solution notebook. This notebook offers an end-to-end pipeline from data loading to generating the final submission file. It's a fantastic example of how to approach a transfer learning problem in a practical setting. So, this challenge uses Raman spectroscopy to predict concentration of glucose, acetate, and magnesium sulfate. The core problem is transfer learning, building a model that works across different Raman devices, especially a new unseen one. We train an over 2500 spectra from 8 devices and test on a single 96 well plate from a new multiplexer. Evaluation is based on the R2 score. The solution notebook provides a complete end-to-end pipeline. So this step cleans raw data, handling formatting issues and converting to numeric. It isolates training data and leverages dual spectral scans to effectively double the training dataset size. And then the core is the Raman exception model, an adapted exception CNN. It uses the phi separable convolution for efficient feature learning and residual connection for deep network training stability, leveraging optimized hyperparameter. And then a custom Pytorch dataset prepared data. It performed curical normalization and convert NumPy arrays into Pytorch tensor with the necessary channel dimension for CNN input. So the model is trained using Adam optimizer and MSE laws for prediction. It averages result from dual scan per test sample for more stable and accurate final prediction. Then format from them submission. Let's brief touch on the code structure. So the first, extension imports for Pytorch data handling and math. Second, a custom residue block with a learnable skip connection for flexible learning. And a simple pass-through layer for skip connection. Initialize the main model with various architectural parameters. Construct the network first layer with ID convolutions and downsampling. Implement efficient device separable convolutions for feature extraction and downsampling. And then contain multiple residual block for deep feature learning without changing spectral dimensions. So the further reduce spectral dimension using device separable convolution, preparing for final layers. Flatten convolution output and processes it through dense layer for final prediction. defines the data flow through convolution and fully connected network. So handle data loading, curical normalization and conversion to Pytorch tensors. Then reads, cleans and reshape raw data, preparing it for the dataset. Configure model channel, initialize the model optimizer and learning rate schedule. So manages the training loop including batch processing, gradient updates and learning rate adjustments. Generate prediction on test data, averaging dual scans for robustness. Or straighten the entire pipeline: data loading, model setup, training, and prediction. This solution effectively tackles transfer learning in Raman spectroscopy using a specialized CNN and a well-structured pipeline. It's a great example of robust ML for scientific applications. In this video, I am going to walk you through how I use Notebook LM, an AI researcher assistant developed by Google, to explore and understand my PyTorch course notes. Whether you are a student or researcher, Notebook LM helps you organize, summarize, and interact with your notes in a smart way. So first I uploaded my PyTorch course notes to a Notebook LM. It immediately processed the document, highlighted important section and created a structure overview. This feature is really helpful for quickly identifying key parts of long notes or chapter. The interface is clean and adding documents is as simple as uploading a Google Docs or PDF. So next I tested Notebook LM by asking it researcher-based question. Here, what I found most helpful about Notebook LM. It instantly summarized complex topic. It answered my custom question in real time. It helped me focus on understanding instead of just reading. And it saved a lot of time while reviewing technical material for students like me on working on AI and machine learning. This tool is a huge productive booster. And in this part of my weekly update, I will share the two VS Code extensions I explored this week, Prettier and Material Theme Kit. So first I explored Prettier, a code formatting extension. It automatically cleans and organizes your code. I tested it on a messy Python function, and with just one shortcut, it fixed the indentation and made the code neat. This is very helpful for beginners like me who want to write clean code without worrying about spacing and alignment. So next I tried the material theme kit. It changes the complete look of VS Code. I personally liked the material ocean theme. It was soft on the eyes and made the coding environment more enjoyable. This may not affect your code, but it definitely improves your experience. Now, both of these extensions made coding easier and more comfortable for me. In this video, today I will share how we use data science to predict road accident in northern Pakistan and how I played my part using web scraping from YouTube with Apify. So the goal of our project to build a weather-linked accident risk prediction dashboard for the dangerous mountain road in Gilgit-Baltistan. These routes are risky especially during snow, rain or fog. As part of the data collection team, my specific job was to collect real accident cases from YouTube. Why YouTube? Because many accident videos are shared by news channel, tourists, or locals and they contain valuable data such as location, date, weather conditions, and severity of the accident. But manually watching and writing down this data would take too long. How I did it? So I use Apify, a powerful web scraping platform. I created a custom scraper that searched for keywords like Gilgit road accident or Kawan snowfall accident on YouTube. My scraper extracted video title, upload date, channel name, view count, link to the video. After that, I manually reviewed the top video to identify the exact location and weather condition at the time of the accident. This real-time data was later merged with weather APIs like Open Weather Map to build a strong dataset for prediction. This task taught me how to use Epify for automated web scraping, the importance of cleaning and verifying real-world data, how non-tradition sources like YouTube can help in data science for social good. Our final dashboards know accident risk by region and weather, and even send alerts when risks are high. So my small scrapping task played a big role in building a life-saving tool for travelers and rescue agencies. If you're curious about FFI web scraping or how to contribute to real-world data science projects, feel free to ask in the comments. Thanks for watching.